So, but the interesting thing is, this particular driver is probably what they consider RS-485 driver. So there's one pair of wires that's acting as both transmit and receive. Now it's half duplex, so this side can only transmit while this guy is listening. And if this guy wants to transmit, he has to wait till he's done, and then they reverse the bus, and he becomes a transmitter and he becomes a receiver. Now there's other arrangements of this where you have 4 pairs of wire, where this pair always transmits in this direction, this one always transmits in this direction, and then you can get to what's considered a full duplex, where both sides can talk at the same time. This particular pin on this part is what tells this chip, am I a receiver or a transmitter right now? And currently, at least one connection is wired out to this connector. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's no connection on the back there. But there is a connection on the back of this chip. So my guess is, however this decides who's the master, sends a signal to the other end to say, hey, I'm transmitting right now, get off the bus. And that's how they negotiate who's sending and who's receiving. Fortunately, this wire is like right in the way. Now, I'm pretty sure that's going to come somewhere into this. Okay, so that signal comes into this guy. That is the UART. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I think it was about 24-ish. 24, 23? 23. Pin 23 of the UART. So pin 23 of the UART is RTS, ready to send, which is an output, I do believe. Let me just find it on this little diagram here. Yep, RTS is an output. So the UART, when he's ready to send, RTS, he drives that signal low, which then puts him in transmit mode. It also sends a copy down the cable. So I'm guessing the other end of this thing that connects into, there was a twist in the cable such that came in on, one of the other control signals on the UART, so it could do some handshaking where it go, hey, I'm ready to send, and then the other end would say, yep, you're clear to send, and then they'd start sending data over the single differential pair. So that's that connection. 1, 2, 3, 4, 5, 6. Pin 6. 2, 3, 4, 5. Okay, 6 is that enable jumper. So this was hard pulled to ground, but it goes other places as well. So let's see if we can figure out where he goes. Okay, he goes into the UART as well. Getting close. Okay, 1, 2, 3, pin 3. Or 3 up from the bottom. 1, 2, 3. Clear to send. So, apparently, Now that's interesting that there's a way to strap clear to send, which is an output out of this guy, I do believe. Yep, pin 3. Clear to send. I wish I had a better version of this, but I don't. Nope, clear to send's an input. So when this jumper's in place, it basically ties the clear to send input low, so it always thinks it's clear to send. Why they did that, that's a question for software. These flow control pins are just a register of bits inside this chip, so you can enable it so that it has some effect on the function, internal function of the UART, but for the most part it just lets the CPU see what the bits are doing, and then it makes the decisions on whether or not to go ahead and send the next byte or not. That's clear to send. Okay, let's go on to the next one. 6, 7. 6, 7. 7 goes to resistor to ground. No connection on the top side. Again, just another random resistor to ground. Only thing I can think of is this somehow affects control signals on the opposite end of the cable. So this ties it in the good state, and when you plug the cable in, the other end detects it and off it goes. 8. 8's on this side. Where does 8 go? Okay, 8 goes to there. Another thing those two resistors could have been, I kind of doubt it, is they might have had a full duplex version of this chip, and that was part of termination for the full duplex chip when it's not used. But the fact that they're so spread out on the connectors sort of makes me doubtful. Okay. Pin 2 and 3 are A and B, which is the differential input-output port, the A side and B side. So, there's one side, and I bet you the next one over is the other. Oh, lost that bet. Oh, these are quite spread out too. So it might be that this is termination for a full duplex version of this network. They might have had similar cabling for multiple styles or signs with multiple channels, and that's what they were there for. So these two pins are decoded. Move on to the next one. So 1, 2, 3, 4. 4 goes to that. Which then gets traced through to this resistor. Now that might just be a pull-up, and it is. So there's a 77.4K pull-up, so I bet the back side of that resistor goes somewhere else. It does not. Oh, it's underneath it. It's that trace right there. So it does go inside of that pin grid. So what I'm watching for here is when I get close, I'll see a big dip on the meter before it actually beeps. Whoop. Right there. 1, 2, 3, 4, 5, 6, 7, 8. 8 pins up. Just minimize that for now. Data send ready. And data send ready is an input. So again, this is part of the handshaking to let let both the UART and the processor know that the other end's either ready for data, ready to send data, or what the heck's going on there. And typically all these signals are just going to stop at this chip. They're not going to be multi-drop, because this chip is going to act as the buffer driver for it and store the state. Okay, so that was 8. 9 is ground. 10. 10, I bet you... That's another control bit. 5. 1, 2, 3, 4, 5. Data transmit ready. So that's an output. So this connector had 2 pull downs, a RS485 single channel differential pair coming out of it, all 4 control bits off of the UART, and that was about it. I mean, there was no other secondary communication channels that I could find. Now let's go back to this chip and find out where the last of his pins go. So data in, DI is data in, RY is the output, DE is data enable. So ground power, these 2 should go back to the UART. He might be, oh, he's going to have to be active, but he might be tied to pin 5. These are typically inverts from each other, so in this case, data enable is active high. So when it's high, it's pushing stuff out the bus. When it's low, the bus is tri-state. And RS, when he is high, he's taking data in from the bus, and when he's low, the bus goes high. When he's high, when he's low, This chip, they are not inverted from each other. They are both active high. So when the enables are high, it either pushes data out the bus or it takes data from the bus and puts it out the chip. Very interesting. So I expect DE. And we'll just start in the corner and work our way around. So first pin's power. Yep. Next pin's data enable, which I expect to go back to the UART. But it does not. It goes to 74 LS93. Things are starting to get a little funky. Nope. Eyes are just playing tricks on me. It actually went back to the UART. 1, 2, 3, 4, 5 up from the bottom. So 5 up from the end. And of course, I closed that window. So let me open it up again. Do that, do that. 1, 2, 3, 4. And that's DTR input. So that matches what the other one. They're using the flow control outputs from the UART to control the state of that transceiver. Okay, next pin over. Goes to pin 3. Receive input pin 6 goes to pin 3, which is receive. Hey, or I should say receive output goes to receive on that chip. So that matches up. RS, we already proved out where he goes. That leaves me ground and data in. And data in should go to transmit, which is... Where is transmit? Pin 9 maybe? TXD, TX empty, data bus, right, chip select. Oh, TXD, yep, pin 19. So first and foremost, let's check the ground, because that's easy. And this pin here should go to pin 19. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And it does. So, we've proven all the connections between here go to here and here. Now, I can continue to probe this chip and see where he goes out as is. But if you look, we got this massive, nasty, not super nasty, but this massive tangle of traces in here. So it'd just be easier if I can pull this chip and its socket up and then trace it through when I don't have it in the way and trying to steer through it. I'm also going to get rid of this chip since I'm going to be soldering anyways, and these two resistors and that resistor. Again, they're not used, so we should be good. So, onward and downward. Before I move off this bench, I'm going to pop this chip out of the socket since they were so nice to do that. And ta-da! A vintage, original Intel 8251 UART chip. Not many of those around anymore, thankfully. Now, the UART chip, the basic guts of that UART, is still in use today. It got sucked into bigger UARTs with more features and functions, and then sucked into Northbridge, Southbridge, and little USB to serial dongles. But the basic register step that makes the guts of that chip work is still in use today. Okay, so I want to pull him. Okay, got it. Oops, screwdriver.